Welcome to the course on fundamentals of MIMO wireless communications. We are currently discussing the small scale propagation model. We have seen multipath interference model. We have seen the distribution of the envelope of received signal. We have also looked at the distribution of the square envelope of the received signal, and we will look into the received signal correlation in today's lecture. Now, before we proceed with the discussion on correlation of the received signal, I'd like to remind you a few things, like when we have considered Rayleigh distribution for the envelope, that is alpha, which is equal to mod of h of t, we would like to remind you a few things, like we have assumed flat fading, and when we said h I of t, that is we said that h of t is made up of h I of t plus j h q of t. If we look at h I of t that we have explained before, it is sum of n components including cos phi n of t. So, when we arrived at Rayleigh, we assumed that this is Gaussian distributed following central limit theorem, and that was true when the number of paths that arrive were pretty large, and we had assumed, or we had considered flat fading when these paths which are different all arrive almost at the same time. So, what we effectively mean is, suppose there is a transmitter which we indicate by a T x, and there is a receiver which is indicated by R x. So, there are n number of paths between the transmitter and the receiver. This we should always remember, there are n number of paths. However, the propagation delay for these paths are almost the same, and that would happen if these are at the two focal points of an ellipse, where the reflectors or scatterer or the objects on which the signal impinges and gets dispersed, they lie on the ellipse whose two focal points are the transmitter and the receiver. If we have this, then we can say that there are n number of paths, very large number of paths, and they are all having this tau n for n equals to 1 to capital N almost equal to tau cap. And this led to the conclusion that we could have flat fading, because our expression of h t, we had sum over h n of t delta tau minus tau cap, and then we could add up all of this to represent h t comma tau. So, h t comma tau was h t times delta tau minus tau cap. This led to flat fading. However, there are very large number of components which get added up, because of which we could make the Gaussian approximation, and for which we have got the Rayleigh distribution. So, this is one of the things which we would like to remind you. The second important thing which we would like to remind you is that when we derived these expressions, we said that let s tilde t is equal to 1. So, when we said let s tilde t be equals to 1, what we meant was s of t was cos 2 pi f c t, or the carrier tone itself, which means that we are sending a constant amplitude tone in the frequency axis. However, when it is received across the band of interest, it was flat, but this amplitude that is received is fluctuating. It is fluctuating with time, and therefore, we have h of t, h I of t and h q of t, or we have h of t time varying, and what we have said is it is time variant. What we have also seen is that this variation can be well characterized as it is a random variation, and we have also seen that this received signal could be represented as this was r tilde t when s tilde t is equal to 1. When this is Gaussian distributed, we have seen that. So, this random distribution is Gaussian distributed for the special case, and we have also seen that this received signal can be represented as the outcome of a linear filter. So, what we have effectively the channel as randomly time variant linear filter. So, even though we have sent a constant amplitude, the received signal amplitude keeps on fluctuating dynamically, and this amplitude fluctuation can be described in one instant by a Rayleigh distribution. In another instant, we said that it could be Rician if there is a strong line of sight component present, or if there is one strong specular component. Suppose there is a excellent reflector which converges the energies, so they go there. So, when there is a specular component instead of Rayleigh, what we get is the Rician distribution. If there is a specular component, so alpha, which is mod of h t, is Rician distributed. That is what we have seen, and we have also described that the distribution would look like the one we have here, and for the values of k as in this particular figure, when k is equal to 0, that means the weight of the Rician component is 0. That means, where there is nothing in this particular specular component, then we are left with all reflected paths, and what we end up is with a Rayleigh. However, for non-zero values of Rician coefficients, for 0 we have the distribution following Rayleigh. For non-zero values, the distribution as the coefficient increases slowly becomes narrower and narrower, and it peaks. So, when k tends to infinity, this will become very, very narrow, almost concentrated in one place, and rise very high peaks, which would mean that there is hardly any variation of the signal, which is denoted by x. So, when there is a very, very strong specular component compared to others, or we can say that between the transmitter and the receiver there is a very strong specular component, whereas the reflected paths are very, very small. There are hardly any signal strength available in the reflected paths. In that case, what we have is a Rician distribution, and in that case, when these are almost negligible, that means, when this is infinite in ratio with respect to the powers in this, there is hardly any fading. So, we said last time you could almost imagine this to be an AWGN condition if there is only additive white Gaussian noise, or near to ideal condition with a signal strength. And under these conditions, earlier we said that Hi is 0 mean, Hq is 0 mean, but in this case Hi is not 0 mean, but there is a certain Mi, that is a mean associated with I component, and a mean associated with a Q component. So, what we see is that there are two different kinds of very prominent distributions that usually would appear. So, to have a uniform model, what was done is the Nakagami distribution was proposed. So, Nakagami distribution is the one which is depicted by the expression as shown in this particular one. So, P of alpha, alpha is mod of h. So, that is the envelope is 2 m to the power of m, x is basically the variable, random variable 2 m minus 1 by gamma function, gamma of m is the gamma function, omega p is the power of the received signal e to the power of minus m x squared by omega p for m greater than half. So, with this one could describe different distributions, whether it is Rayleigh or Rician, by choosing appropriate values of m, and that is one important reason why Nakagami-m is very, very important. So, in this model if m is chosen to be 1, if you take this particular case, this distribution would resemble that of a Rayleigh distribution. You can clearly see m to be equal to 1. This would become equal to 1. There would be x e to the power of minus x squared by omega p, and whole expression like x divided by omega p, m is equal to 1, e to the power of mx squared, e to the power of minus x squared by omega p. So, that would be a Rayleigh distribution. For m equals to half, it would look like a Gaussian distribution. Again, you could clearly see m equals to half means minus x squared by 2 omega p, and rest of it would turn out. So, this will be a one sided Gauss distribution. For m equals to infinity, there will be no fading, just like the Rician distribution, and the Rician distribution can be closely approximated by Nakagami-m by relating k, that means the rise factor, to the Nakagami shape factor, which is the m in all these expressions. For example, if you would take k equals to this particular expression, square root of m squared minus m divided by m minus root over m squared minus m, for m greater than 1, you could map a value of m corresponding to a certain value of k. So, if I would choose m equals to 1, I would get a Rayleigh distribution, and if I would choose m equals to this particular expression as given in the one below, I can get Rician distribution corresponding to that particular value of the rise factor. So, using a single expression, we could get the distribution of envelope for either Rayleigh or Rician. The advantage is why we are studying all these kinds of models. The importance of all these kinds of models is that we would like to design transmitters and receivers, as we have been saying. So, design the transmitters and receivers, you would need important performance metrics, and to get this performance metrics, we would often require these to be analytical expressions or closed form expressions. So, for Rayleigh, we have seen the expression is quite easy, quite simple, and you could get insights, whereas for Rician it is not so. Whereas, if we look at this particular expression, again this could lead to closed form expressions if we use this for calculation of, let us say, bit error rate expressions, and using one result we could choose different values of m, and that would give us the performance for Rayleigh case or appropriate Rician case or even no fading case. And in this figure here, this diagram shows the different distributions for different values of m, and clearly you can see for m equals to 1, this one looks almost like the Rayleigh distribution, and as the value of n increases, this density function becomes more and more constrained within small range of x, as well as there is peaking. And if we would look at the previous PDF for Rician distribution, we see they are almost similar. So, that is the advantage of Nakagami-m distribution, and it is often used in study of wireless communication systems. Now, last note regarding this particular part, that means k equals to root over m squared minus m, and so on and so forth, with maps k to m and m to k, we have to be a little bit careful. So, this particular figure shows the distribution of the square envelope of gamma density function, and on the x axis is the variable x, whereas we have two different kinds of lines. One is the dashed line, one is the solid line. So, but there is the same legend, that means the star, there is the circle, and the square and the triangle used in the dashed and the dotted line. The dashed and the dotted line correspond, one for the Nakagami-m distribution, the other for the Rician factor. So, even though we use the corresponding mapping as given over here, that means even if we use m and k matched to each other, when we look at the corresponding distribution, what we find is that if we look at the actual Rician distribution and if we look at the Nakagami-m distribution, so there is a gap between the two distributions, especially towards the cell edge. So, we would clearly identify the gap, and this particular result is for m equals to 2, but as we increase the rise factor, this gap decreases. So, when it is closer to Rayleigh, the gap is larger, as can be seen in the upper portion of the distribution also. Now, amongst these, what is more important is this tail probability distribution for communication systems, because we are often interested in calculating the outage probability or probability that signal will be below a certain threshold. So, when we do that, what we should remember is, if we are approximating Rician distribution by gamma distribution or Nakagami-m distribution, what we would find is that there is a gap towards the tail which could lead to certain erroneous values in the outage probability calculations. The error is sometimes very significant because we are looking at the tail probability. So, we have to keep this in mind when we are using Nakagami-m in substitute for Rician distribution. Right. So, with that we move ahead and we take our discussion to the signal correlation. Now, why do we look at signal correlation? Because we have already said that what we have is a randomly time variant linear filter whose coefficients are given by h of t. So, h of t is random, although there is a constant amplitude signal that has been sent. So, to study a random variable or a stochastic process, we need to study it in multiple dimensions. So, one of the ways to look at it is the distribution function. We have already looked at the distribution function, and we have said that under certain circumstances, when there is no line of sight, only non-line of sight is present, what we generally get is the Rayleigh distribution. However, if there is a strong specular component, what we get is the Rician distribution. So, under non-line of sight there is Rayleigh, under line of sight there is Rician, and these are the two most common distributions that we encounter. And we have also discussed the Nakagami-m distribution, which can be used to analyze both the Rayleigh case as well as the Rician case by choosing appropriate value of the shape factor, that is m. Now, after looking at the distribution for this particular random process, what we also need to look at is the correlation properties, because it is time varying. So, if it is time varying, we need to look at what is the characteristics of time variations. So, to do that, we need to look at the correlation properties, and with that we will be able to define the behavior of h of t, which is the objective of the next part of this particular discussion. So, if we look at the signal, so if we look at the received band pass signal correlation, we could write phi of r r of delta t is equal to expected value of r of t times r of t plus delta t. So, this is the basic expression for the correlation. What we will go through in the next few minutes is go through the steps from which we could find this, which would lead to a very important result, that is the coherence time of these kind of channels. So, if we expand this, I would put this equal to sign here, because that would help us have a lot of space over here. We would expand r of t. R of t would be h I of t cos, instead of writing 2 pi f c t, we will write omega c t, just so that it helps us reduce the space, omega c t minus h q of t times sine omega c t. So, that is the first component. The second component is h I of t plus delta t cos omega c t plus delta t minus h q of t plus delta t into sine omega c t plus delta t. So, that is we have r of t, which gets expanded in this part. R t plus delta t is basically r t, but this t has been replaced by t plus delta t. So, what you see in these two expressions is they are exactly the same, h I t instead of h I of t, h I of t plus delta t, cos omega c t, cos of omega c t plus delta t, h q of t, h q of t plus delta t, sine omega c t plus delta t. So, in the next few steps we have to expand this expression, do all this multiplication, collect the terms, so that we are able to apply the E operator and get to our appropriate result. So if we would expand this expression, we still have the E operator. E is the expectation operator, which we keep it outside. We have hi of t times hi of t plus delta t cos of omega ct times cos omega c t plus delta t. That means we have taken these two products plus, so we now have this two products h q of t of t plus delta t. So which you can identify, we are basically multiplying these two terms, and we have the sine and sine term, sine omega ct times sine of omega c t plus delta t. Okay. And of course there are the other terms. Next we have hi hq terms, hi of t cos of omega ct, hq of t plus delta t sine of omega c t plus delta t. This product is done. Now we will be doing hq hi, this term. So again there is a minus sign, hq of t sine omega ct. I am writing this in short, hi of t plus delta t into cosine of omega c t plus delta t. So now we have all the expanded forms. So what we see, there is a cosine and a cosine, and there is a cosine and a sine, there is a sine and sine, and there is a sine and cosine. So we need to use our laws of trigonometry. So we just summarize them. We have cos a times cos b, I am writing it in short, is equal to half of cos of a plus b plus cos of a minus b, and we have sin a sin b. We will use these results, cos of a minus b minus cos of a plus b, and we have sin a cos b is equal to half sin a plus b plus sin of a minus b. So using these, like we have cos a cos b, we can apply this expansion, sin a sin b, we can again apply this, and so on and so forth. We will be able to reduce this expression. So as we go ahead with this expression, we would still keep the E operator. So we have hi of t plus delta t. So we have cos cos a cos b. So we are going to reduce these expressions to half cos a plus b and cos of a minus b. So we are going to have cos omega c 2t plus delta t and cos of omega c delta t. Sorry, we are going to have plus E of hi of t hi of t plus delta t into half cos omega c delta t plus expected value of hq of t hq of t plus delta t. I'm covering this up so that we can follow from whatever was in the previous lines, into half cos omega c delta t minus E of hq of t hq of t plus delta t times half cos omega c 2t plus delta t, and then we continue to have minus sign because of this minus expression. So what we have is E of hi of t h q of t plus delta t, and we will write in short in this occasion, that is sine omega c 2t plus delta t plus sine omega c delta t, and the last expression again we will combine h q of t h I of t plus delta t half sine omega c 2t plus delta t minus sine of omega c delta t. So with this we have been able to capture all the components of the product of this particular line that are there. They would open up into these, and then we could collect all the terms which are together. That means we could collect this particular term, we could collect hi cos omega c t, and we would collect hq cos omega c delta t, because there is cos omega c delta t and there is hit plus delta t, and we could also collect the terms which are associated with cos 2t plus delta t. We would also collect the terms which are associated with sine delta t separately and this separately. So if we do that, the expression what we end up with would be E of hi of t hi of t plus delta t plus E of hq of t hq of t plus delta t, this whole thing having the coefficient cos omega c delta t. We also have E of hi t hi t plus delta t minus E of hq of t hq of t plus delta t with half cos omega c 2t plus delta t, and then we have the other terms, that is E of hi of t hq of t plus delta t with a minus sign in front of it plus E of hq of t hi of t plus delta t, this having with it sine omega c delta t, and then finally we are left with the last term, that is minus of expected value of hi of t hq of t plus delta t plus E of hq of t hi of t plus delta t multiplied by half sine 2t plus delta t. So we have arrived to the expression which is of interest to us. So this particular expression we have been able to separate the terms, the one where the cosine component is without the t, it is having only delta t, and then we have the terms which have the t component, and there is also the sine which has the t component, and we have the sine which is omega c delta t. So we stop at this point in this particular lecture, and we will continue with this expression to derive the expression of correlation of the received envelope using certain properties which we will be able to describe very soon. Thank you.